So once again, thank you for accepting this conversation. I'd like to start from my perspective and how we can bridge the gap starting from there. So I'm an aerospace engineer, and I'm looking in the way in which computer science is influencing my field, and I can see now in my field that the trend is going towards Python. So we're really leveraging the open source way of thinking of the computer scientists. We're starting to do that now, last 10 years, let's say. And now there's also Julia, let's say, in the field. So could you explain how is Julia different from Python? Why should an aerospace engineer or an engineer in general think about using it and
Yeah,
things like that?
one of the main things about Julia is that it is a language such that it is high level and it is fast, right? And the reason why that is nice to have is that you don't need to be writing your low level library code in another language, right? So all the differential equation solvers, they're written in Julia. I mean, there are some that are wrappers to existing packages just because those packages existed, but the actual most high performing versions are the things that are just pure Julia codes, right? Um,
Okay.
and what this means is that you can get some very weird features for free without even trying. So, for example, the GPU support in the differential equation solver library actually comes from zero code. It
Mm-hmm.
doesn't require any code to get GPU support. There is automatic differentiation support that is done by default, and then I mean there's extra stuff that's added on top of it as well. But if you don't write code, you can still get features, and it's a well, you cannot write code and still get features, and those features will be as fast as C code.
Right.
It takes a little bit to really understand how to write in those styles, but once you understand the correct generic styles, then I mean,
Okay.
the world is your oyster. There's a lot you can do.
And was this part of your goals? I mean, why did you said, okay, we don't want the Fortran wrapped around in our code to run a differential equation solver? Why?
Well, I do research in the numerical methods, right? So I mean, I wanted to be actually. I mean, I can't just wrap other people's methods. That's just not, also in things like differential equations, right? There a lot of times, there just aren't good methods in a lot of areas, right? And so there's just a lot of low hanging fruit for things to explore, even 100 years into the field. There are ways to be able to optimize solvers for new cases and everything. And I didn't want to be writing Fortran and then wrapping it in R, Python, etc. I mean, it's much easier just to give a Julia package and then just say everything that calls Julia is fine, right? And
Mhm.
so we have R, Python, and Julia front ends for this Julia package, and I could just sit there all day and just interactively in a rep will just be changing the underlying code, and it's just as though I was using Fortran. So
Mhm.
it's a very nice way to get around that two language problem that generally exists.
Right. So it's also easy to call Julia from Python, for
Oh yeah,
example.
for sure, for sure. I mean, yeah, we put together the Stiffy QPy library, which is essentially like about 100 lines of code, and where that 100 lines of code is just installing the Julia packages for you, um,
Okay.
and then it just uses the wrapper, and then it puts a nice documentation on top of it. Yeah, because of the bridges are pretty easy to use.
Right. Okay. And thinking about again efficiency, I know you worked on stochastic differential calculus. Um, can you maybe explain a bit, particularly with the routines associated to stochastic calculus, why are they so well behaving while the performance is so high? I saw you made a comparison between the Julia package and the Torch SDE, if I'm
Mhm.
correct. Can you explain in the details in the implementation? I mean, why is it so efficient?
Mhm. Yeah, so one of the things that really helps out is that Torch does not do very well with its JIT. Torch's JIT is, Torch's JIT is very much centered on the types of problems that you see in machine learning, which is essentially that you can assume that everything is big vector operations, and so there's a lot of things that it doesn't do very well in scalar operations. There's a lot of things it doesn't do well in terms of memory managing, as small arrays, and I mean there's just so many things that the Torch JIT misses. So so a good order of magnitude is actually just because torch is bad there, right? Right. There's nothing else to say, right? So like the there's two aspects to optimizing, right? Well, three aspects to optimizing. There's the first thing is don't do anything bad. The second thing is do a better algorithm. The third thing is do a better implementation, right? Um, so uh, we in the case of the Torch SDE benchmarks, you actually see all three aspects of that, right? So the PyTorch optimizer is not doing very well on that problem, and that's one aspect of it. The other aspect is that there is a implementation that is very optimized for the style or for the adaptive SDE solvers. So um, the naive thing that you can do is you can say, I have a whole interval and I'm going to interpolate this interval to find my Brownian motions. And, that's the way that, these like gains and loins method is. And, that's the traditional way with adaptive ODE solvers or adaptive SDE solvers. And the reason why you haven't seen adaptive SDE solvers in the past is because, you know, even though you can prove that that method has a good like big O, right? So you know,
Mhm.
on average, using uh, on average using what's the word bisection to be able to figure out what point in time you should be using to grab the points to be able to interpolate from. On average, that goes down logarithmically, so you don't have to care, right? But it turns out that if you have SDEs that are size like 50 or lower, then in general the time that you're taking to interpolate that is actually going to take more time than the actual user's F call, right? And so there's like all these little extra little details in the implementation where you have to be like, okay, we chop off that, and the whole algorithm for that is explained for how you can set up two stacks, and if you have these two stacks set up together, then you always know that the next value is going to be the next one in the array because everything is aligned in the arrays. You get SIMD and all these extra details, right? So there's these
Right.
implementation details, and then there's the algorithm details where Torch SD still doesn't have some of the highest 1.5 order adaptive methods for et cetera, et cetera. So when you put all three of those together, you do see a pretty wild difference, right? But it's really one order of magnitude is this, one order of magnitude is that, one order of magnitude is
Mhm.
that, and when you break it down, it's actually quite straightforward. Why you'd actually expect to see that difference.
Okay, and was this coming out of? I mean, were you chasing? I don't know the history. Were you chasing Torch SD, or I mean, were the considerations that led you to such an efficient algorithm coming out of your PhD as well? I mean, years before even being able to do the comparison.
I mean,
And
yeah,
did
it
you?
was like five. It was made like 4 or 5 years before Torch SD. The only
Okay.
reason um, why the benchmark existed was actually someone posted that benchmark in our chat channel. They were just like, uh, "Is this true?" And then I was like, I tried to run it. I was like, "Yeah, it is." And they're like, "Okay, then you should share this because nobody knew that there was much of a difference." I was like, "Okay," I just plop the code on the internet, right? That's actually how a lot of our benchmarks show up, right?
Yeah.
If you look at the DiffyQ benchmarks, there are benchmarks that are generated by us, and normally the ones that generated by us are the ones that you'll see in the papers, right? So you'll know it's the one that's like top down benchmarks. If it's something that comes from either Harris book, so the classic method, classic benchmark equations like the Bruselator, um, the Rober equation, like these ones were like, okay, we're going to implement these because everyone benchmarks on these equations, and we're going to make sure that we have good implementations, right? And then for the SDEs, you know which ones are the benchmarks that were used when creating the library because those are the ones used in the paper. Um, Everything else is really user driven, right? We generally see users come to chat channels and they say, hey, look, this is the benchmark that I'm seeing, and so then I say, could you contribute these benchmarks to SciML to benchmark so that way we could
Mhm.
track it over time and share. Sometimes we do good benchmarks, sometimes we don't, right? And
Right.
I think a good example of that is the filament benchmark for a very long time was one of our antithesis benchmarks. Filament and BCR. Those were both accepted into the SciML benchmarks repo because we wanted to track their timing because we were not doing well on those benchmarks, right? Now, if you look at the filament benchmark, you'll see something that's fairly interesting is that there's this very specific type of algorithm that is a it's explicit, but it has a really large stability region, so it's made for semi-stiff for semi-stiff equations, and that's the one that actually performs the best on filament for quite a large range. And then on BCR, we've really tuned our SDIRC and our sparsity handling over time to be able to, be able to be most efficient on that one too. But a lot of these benchmarks start out as challenge problems where someone comes
Mhm.
to us and says, you know, you're slow here, and we go, we are, yeah. So add it to the benchmarks and do, and so it's kind of interesting then because it's we the reason why the library has gotten so optimized is because there's 50 people who have or well 50 people are kind of active on it, and more than 100 people have contributed to it, and there's just this culture of everything should be fast, or if it's not, if something's not fast, then it's a bug, right? Like we treat any bad performance as a bug, and we treat every single user um, you know we treat every single user report about efficiency issues as a bug, right? And so that's a very different way of doing it from something like LSODA or CVODE. Like the older ODE solvers, right? They wrote the
Mhm.
ODE solver, and that was kind of the version, right? There was updates that were kind of done. Like they had like small pre-releases where they shared it with a few people. But remember, a lot of these ODE solvers that you use today, like LSODE, LSODA, were before the internet. So
Mhm.
they would ship CDs to people that they knew, and they'd be like, "Hey, try to find if bugs, try to see if this is good performance." And then once that was done, they shipped the CDs out to everyone, and that's what was set in stone, right? Um, what we kind of have is a bit different because it's live code, and live code where we're seeing more and more and more benchmarks as time goes on, and the methods are just getting more and more refined. So I mean, that's just another difference between the pure Julie methods and the Fortran methods. So, right, they're really part of this open source ecosystem where they're constantly updating and constantly making sure that all the hyperparameters are handling all the different cases. They're adding branches for for these weird floating point behaviors that can show up, and all these kinds of other things. Which so it kind of has the the movement of a web framework, like
Mhm.
keeping up to the day-to-day issues, but it's an ODE solver where it's just like continually making sure that it's continually just looks like it's just solving an equation in the back to the user. So
Mhm. Nice. And yeah, now that we're here, I had a question I wanted to ask you at the end, but I can go on with it now. You mentioned the internet and the revolution. I mean, we're now being able to have this conversation while 10 years ago we may have needed to go to a conference, or even worse, there was no conference which both of us could go because of our interests. So also because you're an assistant professor, no? What's your role at
applied
MIT?
mathematics instructor,
As
it's
instructor.
yeah. Mhm.
Can you tell me how much of this internet-driven approach are you bringing to your teaching?
Oh, so my entire course is online.
Okay.
And so my course and all my lectures and everything have been online. Especially, I always put my lecture notes online, but this year, since I was had the pandemic and everything, I had to give all my lectures via videos. So I just did them as pre-recorded videos, and I just shared it with everyone, and then I kind of supplemented with a lot of one-on-one kind of discussions. So I actually what I kind of did with it was I made it more like, here's the lecture series, here's the homework they have to do with the lecture series, but for each of the students, now let's treat this like treat this like a research relationship, right? Because it's a graduate course. So let's one-on-one, let's walk through these issues. And it was the homeworks are made to be difficult, and the homeworks are made to be such that if you do the homework, then you know everything about the course. um, but then it's like, here I'm on Slack, I'll Slack with you all day long. Let's it's less about trying to like prove that you know it than to get you to the end, which is kind of like how a research advisee kind of situation is, right?
Mhm.
um it's less about the examination, more about, okay, let's get you to something that's working, so that you write all the code, but um mostly because I'm lazy, right? Yeah, but but like I'm helping you every step of the way, because what I want you to get to is I want you to have written ODE solvers with forward modes and adjoints and solving neural ODEs all from scratch on your own, right? Um, and that's kind of the point of the course, and it kind of worked out really well doing it in this internet kind of way. I don't sleep very often, and so what it meant was that, with the pandemic, people were all around the world, and it didn't matter what time zone people were in. We could really have these like one-on-one chats through Slack, and with the Zoom added in and everything to really, I feel like it worked better than a normal course.
Mhm.
So yeah, I
Yeah,
mean,
if I'm
yeah.
not wrong, I recall you saying that your plan is to then maintain the videos as references in the lecture, and then doing lectures in presence, and your role will be just to comment. And
Yeah, I
I
mean,
see a parallel between this and the way in which you're coding. I mean, the ODE is that's always
mhm,
the same. The topic of the course is always the same, but
mhm.
there's this updating uh,
Yeah, I mean,
aspect.
that's why I think that my entire workflow has kind of gone into this zone, right? Where it's like, you use version control and you use the internet, so that way you can broadcast, like, here is the version of everything that's going on. And then you talk with everyone to be able to, like, there's this immutable record, like, almost like the blockchain, right?
Okay.
It's like as it grows, it keeps on growing, and you're just like, it just gets better and better and better. And then you use the fact that that's out there to basically say, let's not spend time on me telling you how an adaptive ODE solver works. That video exists. Um, if you think that video sucks, like, tell me, like, I can make a new version of it, right? We can update this. But like, if I ever hit that part, I just say that already is online. Let's do the next thing, and then there's this like immutable record that keeps on growing and growing and growing. Um, and that exists in a lot of my that exists in a lot of my teaching, then also in a lot of my research as well, right? Because my research is pretty intimately tied with the differential equation solvers and the scientific machine learning tools that I do. And there's this immutable record of Stack Overflow posts and discourse posts, and you know most people that I meet these days, they kind of go, oh yeah, yeah, I've read one of your discourse posts before. And I mean, I think that there is probably around like 10,000 or something ridiculous internet posts that I've done, explaining, like, oh, like, this person had this problem, oh, the solution to that is here. And so if you type in like Julia, differential equation accidental derivative 0 or something, like, you'll find an answer. And so yeah, so I think that this mixture of like, and a lot of those questions are then staged, right? Because it's like, what I mean by staging is that someone comes to the chat channel, right? We work out this whole problem, and then I go, this should be recorded, right? Because
Mhm.
if someone's going to hit the same issue as you, and this was something that we should be able to make sure is Googleable. And so take the chat, and they'll ask the question in a nice form on Discourse. I'll give the answer, and then boom, now it's online, right? And so in that same way, it's this like mixture of doing one-on-one with an immutable record of the internet. So
Right. Nice. I have another question I wanted to ask at the end, but you mentioned the blockchain.
yeah.
So, uh, are you interested in the cryptocurrency world, and are you an active trader? Are you using your algorithms for doing something about that? Are
Oh
you
no,
playing?
I keep that world separate. I don't. The only interest in crypto that I truly have is the connections to federated learning and scientific machine learning. Basically, there's a lot of issues that people have in many different domains. So there's a group that I'm doing agricultural scientific machine learning,
Okay.
and there's a group that and then everything that I do with pharmaceutical modeling and simulation too. There's always this issue with sharing data, right? No one wants to share clinical trial data. No one wants to share data on all of their assets, and so you want to be able to do scientific machine learning and these kind of training algorithms without sharing data. And that's my closest. I mean, that is my link to crypto. So there's things like
Hmm.
uh, homomorphic encryption and federated learning that kind of mix in and have ideas of crypto in there in some senses. But other than that, I kind of I kind of section off my math life from my finances. I you know
Hmm. Okay.
my way of thinking of finances is, if you just do more and more work, then just spawn more and more companies, hopefully that's going to work with it, and you put everything else on the S&P 500. Yeah.
Right, makes sense. So you mentioned the pharmaceutical work you're doing with Pumas. How is it called?
Mhm. Yeah, it's Pumas.
Yeah. Can you talk a bit about your work you've done with it in the context of the pandemic, and also maybe comment on the result of DeepMind's AlphaFold 2.0?
Yeah, I'll say that DeepMind's area is completely different from the one that I'm
Okay.
looking at. The clinical trial pipeline has kind of three stages to it. So you have the drug discovery phase, which is all about what molecules should I be, what molecule should I be creating to be able to hit this area. There's the preclinical analysis phase, which is also known as quantitative systems pharmacology, which is if I was to understand all the reactions, so like A hits B, and then B goes to the DNA, and you have this complex pleb. Can I predict what would happen if I affect the system in terms of the direct reactions and also the side effects? So the reason why that's important is because so a classic example is that amyloid beta is one of the known causes. Well, at this point, some people kind of question whether it's a cause, but amyloid beta is kind of thought to be a cause of Alzheimer's disease, right? So in the drug discovery phase, you might think, well, what I might want to do then is I might want to bind something to amyloid beta to stop it from doing a certain reaction, and that will, then be able to fix the disease, right? Turns out that that's not a good idea in a lot of cases because if you were to look at the systems biology of how everything is interacting, the way to be able to robustly turn down the amount of amyloid beta would be to turn down something that is actually creating amyloid beta, right? Like 'cause otherwise you have these other compensation effects going on in the biological organism, right? And
Mm.
so, this question of what should you actually build a molecule to hit is actually a fairly complex one, right? Because if A binds to the DNA to build C, which binds to the DNA to that that gives you D, but D is the thing that actually looks like it causes disease. Well, should you be building a molecule to bind and basically inactivate D? Do you bind and C? Like what where do you actually bind to everything? And this is the field of quantitative systems pharmacology, which is really trying to say if I was to make a drug that hit this area. Then what would the effects be what would the efficacy of that drug be, and what would the expected side effects be, and how would those expected side effects change over the population? Could we expect some differences in gender? Could we expect differences in weight and all those kinds of aspects? um, so that's quantitative systems pharmacology, and that's one of the things that I do a lot of. A lot of the stuff that I've been doing at American Conference of Pharmacometrics. All my talks have been mostly focused towards quantitative systems pharmacology, and that's been a lot with Pfizer. Um, Now the stuff with Pumas specifically, it's a lot of quantitative systems pharmacology, but then also clinical pharmacology. So the clinical pharmacology problem is much different than the other two because at that point you already know what drug you have, right? So drug discovery is what molecule do I create such that I would hit a certain chemical reaction. QSP is, well, what chemical reaction should I be hitting in the first place?
Mhm.
And clinical pharmacology is I already know what my drug is. I already know its action. I already know all that. Um, but what is the actual correct amount of dose that should be given in a population specific way such that I have a high chance of having efficacy but a low chance of having toxicity? Um, right. When there's that dosing label on your prescription bottle, how does that figure out that if male versus female, you should have these different doses, and if you don't do it like this, then you will have toxicity, right? Well, how is that found out? Well, that's all done through nonlinear mixed effects modeling. It's a form of differential equation model where the differential equation has a model on top of it where you have what's something known as the covariates. So age, height, weight, sex, and these kinds of details influence the dynamical parameters of the differential equation model for how the drug is flowing through the body. And then the problem is to try to figure out how those covariates have an effect on the dynamical system. And then once you understand the relationship between, the predicting dynamical systems from individuals, then you can start to optimize the dose for individuals, given that you know how their dynamics will change. And that's the problem of nonlinear mixed effects modeling. And Pumas is not the first to do this. There's actually been like a Fortran method since like the 70s. Kind of like there is in a lot of domains, but where Pumas really kicks in is that it takes all these differential equation improvements over the last 5 years of Julia, and it puts them all into this nonlinear mixed effects framework where it's a very specific type of problem, because you're always in nonlinear mixed effects modeling. You're pretty much always looking at 10 ODs or less, or 100% of the time is 20 ODs or less. But even then, it's usually 10 ODs or less. Um, they're usually stiff, usually quite stiff because they're chemical reactions. So they have many different, time scales associated with it. Um, so you have to, so a good out, and also there's discontinuities all the time, because every single time you give a dose to the system, you have a discontinuous change in the amount of drug in the body, at least in the first most compartment. So it's this kind of problem which is very interesting for optimizing differential equation solves, because the methods that most people use, like BDF methods like an LSODA and such, those have to keep on going back to Euler's method if you're to use all these discontinuities. So you have to kind of choose different ODE solvers than what's standard. You have to come up with ways to be able to JIT compile, to be able to specialize exactly on the size of the ODEs, because then you can get better SIMD and you can parallelize cross solves and all sorts of extra tricks, so that way you can make that much faster than the naive, like, let's just stick a good Fortran method on a good optimization and call it a day, right? So it is hard to do better than that, right? But you can do better than that. And basically what we've shown with Pumas is that you can do about 3x to 4x better. That's not, when machine learning people talk, they're like, oh, it's a million, it made something a million times faster. This field is well developed enough that you're not going to get a million times faster. But what we do see is that you get something like 4 times faster, and that means that the clinical trials are accelerated. And there's been some high profile clinical trials which have finished very recently, which I cannot mention the names and the details of at this time without the proper press releases from the companies. But there are some pretty big clinical trials that have just finished, and Pumas was a part of making one of these, make sure they hit the finish line at the speed that it did. So it just basically goes to show that 4x faster isn't something that makes a lot of people's like, oh, that changed the world. But in reality, 4x faster means that your analyst is now getting the results back in a week instead of a month, and that really changes the pace at which a clinical trial runs. And so that's been a really interesting problem to be working on, and we're still doing a whole lot with it.
Mm-hmm. Okay, now I see the connection between the Julia environment and your work in pharmacology, because and now I see also the difference with the protein folding problem.
Yeah,
Uh,
and the protein folding problem, I mean, it's about, I mean, the protein folding is more about the drug discovery kind of world, and even then, it's still not quite. Well, I mean, it is for drug discovery, right? Because it's basically like, if we had a protein of this form, then what would the protein actually look like? So that way we can develop another protein to be able to bind into it, right?
mm,
But the place where Pumas is looking at, that drug is already developed, right? So you
right.
can abstract that process
Okay.
away.
Can is it a miscalling saying that what you're doing is chaotic dynamical systems control?
They're not chaotic, but they are a form of control problem. They're kind of like a hierarchical control problem, where what we're trying to do is we're trying to find the optimal control, where the control is the dose, right? So you could essentially, if you frame it as a control problem, it's a discrete control problem, where what you're allowed to do is you're allowed to choose the discrete control, which is the dosing that occurs at finite intervals, and what would the proper dosing be for different individuals, such that you would be able to control each member of the population most optimally. So yeah,
Okay. And
yeah, it's a
do you also touch uncertainty quantification? I work on uncertainty quantification, so I'm curious.
Yeah.
about?
Actually, I put out a method to the ACOP MCS SIG last year, and the papers on that, or actually the preprint, actually just went up this summer. So the preprint took a while to actually get up, but it was about how you can do fast optimization under uncertainty, because the real problem that we
Are you
realized
mentioning
is.
the Koopman operator paper?
Exactly, yeah.
Okay.
Because the real problem and we have a pharma specific version of that paper actually that's going to be going up, because it kind of highlights some different details, and it shows how to do all these types of things within the context of Pumas. And the reason is because it, yeah, I mean it's basically the interesting problem when you're thinking about dosing is that there is no such thing as like the best dose, right? Like, what is the best concentration of drug to have in your body? And so when we're doing this optimization process, we're doing the same thing that people have done for 60 years, and the FDA approves of it. But to me, it always felt a little bit wrong, because there is no optimal dose for you to be me to be able to say, yes, you should be at exactly 250 milligrams inside of your central compartment, and that's the level we want to aim for, right? So the problem that you're actually trying to solve when you're doing um, when you're doing optimization for drug dosing is you're really trying to say there's a therapeutic window. So we know that it's safe for you to have below 250 milligrams, but you need to have above 150 milligrams. Otherwise, it's not efficacious, right? Um, and so it really comes down to there's a lot of uncertainty and there's a lot of randomness going on in chemical reactions. What would be the way to be able to have the highest probability of staying within that therapeutic window? And I mean, the way that people have tackled that problem traditionally is you just kind of, you're trying to optimize to get in the middle of the window with the deterministic model. But what we're doing with the Koopman operator work now is we're trying to rephrase it as, we can incorporate all these uncertainty distributions, because when we do the nonlinear mixed effects estimation, we can do Bayesian estimation and get probability distributions, and then we can start to ask the question, how should we be doing the dosing such that you have the highest probability of being in the um, in the therapeutic window? And it's easy to phrase that question, and people have phrased that question like that before. It's just that the optimization becomes really hard if you're going to do Monte Carlo estimation, right? So think about doing optimization where your actual function call um, is a Monte Carlo method, call that is doing 100,000 ODE solves, right? I mean, that means that if you're going to do 100 steps of your optimization, then you're doing like what, 10 million ODE solves for every single patient. There's no way you're going to do that in practice, right? There's no way you're going to deploy that onto a cell phone, so that way you can get that to the bedside, right? Um, so what the Koopman method is really trying to do is it's just a much faster way that doesn't require doing Monte Carlo sampling to be able to calculate that probability of being within the therapeutic window. Um, and so there's definitely a lot more to do in that space, but it's definitely the direction that we're going, where that problem of how do you optimize the probability that an OD gives a solution, it seems very relevant to a lot of fields.
Okay, yeah, nice. Can we stick on this, because I'm working on uncertainty quantification, and in particular on methods alternatives to Monte Carlo to
Hmm.
be efficient. I don't know if you know, I'm working with polynomial chaos expansion.
Okay. Hmm.
So I really don't understand the difference between what I'm doing and what you're proposing. I don't
Yeah.
know
So
if
so
you.
s- so yeah. So it really comes down to forward versus adjoint types of methods, right? I actually just put a lecture up yesterday for the last lecture of my class. I titled it "Uncertainty Programming" as like a kind of. It's a little provocative of a lecture, because it's no one else would call it uncertainty programming, but there's stuff in there that looks like it's uncertainty quantification in a programming framework, in the sense of differentiable programming or probabilistic programming. There's a way that you can get to doing uncertainty quantification that is actually computationally the same as the way that people do differentiable programming and probabilistic programming. So what you can think about is with uncertainty quantification is that uncertainty the way so So uncertainty quantification, in most of the ways of doing it, right, is essentially you want to try to figure out what the uncertainty distributions will be in the future, right? So one way to do that is, to just do Monte Carlo sampling, where if you sample the distributions of the input, then you get the distributions of the output, right? You can do linear propagation of uncertainties. So, like packages like measurements.jl have a nice way of doing linear propagation, where you assume that all your variables are normal distributions. You define what a function of, what would f of a normal distribution be, like, for sine, cosine, and all that. And then if you recursively move everything down, just like differential programming or automatic differentiation, you define a set of primitives, and you say, I know how to do push forward of uncertainty distribution on sine, cosine, on cube, and all these primitive functions. Then if someone gives me an algorithm, I can push forward uncertainty quantification, the uncertainty distributions, just by doing it step by step by step by step, right? Um, and so measurements.jl does this with pushing forward in normal distributions. And so, in some sense, that is a direct analog of it's a direct analog of forward mode automatic differentiation, except to the space of uncertainty quantification. Um, and so you can actually phrase other methods like polynomial chaos theory as another method in that same vein, right? So what you're doing with polynomial chaos theory is you're creating a representation of the probability distribution, and then you're trying to compute what each of the variables in the process would be in terms of this expansion, right? You normally orthogonal polynomials, but you can also choose pretty weird distribution. You could use neural networks even if you wanted, right? Um, so, but the way that this goes into like being uncertainty programming, though, is that if you can phrase it instead of being about, this doesn't need to be about an algorithm, like, or this could be about an algorithm that changes the code of an original algorithm, right? So, for example, polynomial chaos expansion can be implemented as a number type, or that number represents the orthogonal polynomial, and then you can put that number you could define the algebra on it, right? Where if you had, two distributional quantities, how would they add, how would they multiply, and all these kinds of details. And then you could, in theory, just stick those numbers into an ODE solver, and then you can solve the ODE, and you'd be doing polynomial chaos expansions through the whole ODE solver. And that process is exactly like forward mode automatic differentiation, where it just recompiles the solver instead of be working on floating point numbers, now it's working on, in in forward mode automatic differentiation, it works on dual number algebras. In uncertainty quantification, it works on, orthogonal polynomial algebras. But, in some sense, these are all the same idea.
Mhm.
Um, Now, the thing that we saw was that for the problem that we're looking at, we don't actually need the probability distributions in the future, right? Getting the probability distribution at every single step is more information than you need sometimes. I'm not saying there's more information than you always need, but it's more
Mhm.
information than you need sometimes, right? So for what we're looking at was we only needed this. All that we needed was we need to take expectations of the ODE solver solution, right?
Right.
We didn't. You don't need a probability distribution to calculate expectations, and so you can phrase expectations then as an integral. When you can phrase integrals as inner products, and it turns out that the Koopman operator is then, so the push forward of probability distributions is the Frobenius-Perron operator. But if
Mhm.
you're to look at the adjoint of the Frobenius-Perron operator, that is the Koopman operator, which is pulling back the cost function to the original spot. And so the difference between the two methods is that the Koopman operator method cannot tell you anything about the distribution in the future other than the exact measurement that you did. Right. So, it will tell you this is the expected value this is the expected value of some quantity about the solution, and that's all I know. Like, it will not calculate anything else about the
Mhm.
distribution. Um, but because it's specializing on that quantity, right, and it's pulling back the cost function, this method is then going to scale to, much larger spaces, because it's not actually trying to find the uncertainty distribution of every single quantity of the ODE solver. Um, But so I mean that means that it has similar trade. It's actually very similar to the trade-offs between forward and reverse mode automatic differentiation, though, because then if you care about the expectation with respect to tons of variables, then it actually becomes more efficient once again to have just computed, done the whole push forward, and then just do and then calculate the expectation with respect to every single variable, right? In the same sense that if you want to do if you want the full Jacobian, a lot of times it still makes sense to still have done forward mode automatic differentiation. Um, in a sense, it's the reason why the method works, and the reason why it works so well is because it is lossy in the information that it gives, and
Hmm.
it gives exactly that one piece of information that you want for that one specific problem. And then it basically uses the adjoint of the push forward to not compute what the to basically not compute the uncertainty distributions for anything. So
Okay, I still don't see how you do it. I mean, you're saying you're able to compute the expectation of your observable function,
yeah, you go straight to computing the integral, and computing the integral does not necessarily need the probability distribution of the
right?
future if you evaluate the cost function in the past, and that's
Ah,
essentially the
okay,
method.
I see.
Mhm.
Right. Okay, so you push back via the Koopman operator the the factor inside the integral that you use to compute the expectation, and
Exactly,
then
you pull back that cost function exactly.
once you're
Yeah.
back to the original probability distribution that you are is your input, you're able to compute the.
Mhm.
Okay, interesting. Okay, I see. Okay, can we talk a bit about the SciML work, which I guess is the
Oh yeah.
most
Mhm.
interesting work you've done so far, at least from a philosophical perspective. I have some question about that, but first, can you present it?
Yeah, so where the scientific machine learning work comes from is really that, in a lot of the domains I've been working in, so it's like systems biology and systems pharmacology, what I noticed was that the actual the actual issue is the amount of time that it takes for a modeler to create the model. Um, so we focus so much on runtime, but really, when I actually did my own modeling exercises, the thing that was stalling my own PhD project, and then like these projects with Pfizer and everything, is actually just coming up with a model that fits the data. Right? Like
Mm.
having a faster code does help you come up with a model that fixes the data faster, right? Because then you see your feedback on whether you got the right or wrong answer quicker. But I mean, it didn't answer the real question, right? Because you'd still have to go back to the data, you'd have to go back to the literature, you go and you check read all these biological papers and kind of go, oh, you know what? I think that there might be a chemical reaction right here that I'm missing, and you try it out, and if that didn't work, then you go back to the drawing board, and you keep on going back to the literature, and so a lot of biological models, there's a joke that they're made by graduate student descent, which is really like like each graduate student is like creating one portion of the like when you look at these biological models, like each graduate student is really coming up with like one set of arrows inside of there and really verifying like, oh yeah, this is how this part of the biology works, and if you have enough people doing it, then you kind of get a full model. But um but but that really was pointing to the fact that the real inefficiency was in the modeler. So could we actually use something about the efficiency and the optimization procedures that we had to be able to improve the modeling aspect itself? um, and that's really what led to the universal differential equation approach, because the neural ODE paper came out, and we were working on some very similar things at the same time. And so but what we noticed with the neural ODE work was that it was very not robust for many reasons. Some of those reasons were actually due to stiffness that are naturally seen in biological models, and you need to use different adjoint methods, and there's a lot of work that we're doing in that space. But another big portion of it was the fact that you know, just if you just threw a neural OD on something, it can give you just like a wild result. Like it finds something that's predictive, but a predictive model is not necessarily physical, right?
Mhm.
And so what I did a lot of thinking about was this question of, you know, how do you how would I make the biologist or the pharmacologist happy with my way of automating my process, right? And the first and foremost, the way to make them happy is that every single detail that you and they know about biology or pharmacology has to be true in the model. Like, straightforward. Like the moment
Mhm.
the first thing that if you go back to the FDA regulators or something, the first thing that they're going to ask is like, oh, we know that chemical reaction A binds with chemical reaction B. Is that in your model? We know that chemical reaction B doesn't bind with chemical reaction C. Is that in your model? If you're going to have a machine learning model, you better have that all of those things are true. And that doesn't mean you have to know everything, but everything that we know has to be true, right? Um, and that's really where this universal differential equation idea came in. Where it's like we can, instead of doing a full neural ODE, we can start with a differential equation model, which is the differential equation model that we would have written down, right? But then this process, this manual process of then trying variations of that model is something that we can then automate by saying, well, let's put neural networks in the model, let's do sparse identification of dynamical systems, and do a and basically automatically get symbolic equations out, basically have it give us law tech for what the possible missing terms are. Those missing terms are in the context of biology, they're actually mechanistic predictions, right? Because if you stick a term that says dz dt equals and then dot 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 x times y in that line, then what you're saying is that x binds with y and it somehow creates more of z. um, and so once we have these neural networks in there, and then we can turn those neural networks back into symbolic equations, then that's actually starting to kick out these hypotheses where it's a much easier process now, right? We can have the neural network kick out a full set of hypotheses which says, in order to match the data, we believe that the chemical reaction that you forgot in the model was that x and y are changing z, w and x are changing, and it kind of gives out a list of like, these are the things that you missed. And you can go into literature and you can start typing into PubMed and you say like, Wnt4, BMP3, zebrafish hindbrain, and then sure enough, there's a paper there like someone says that you should have put this in the model in the first place, and that is a much easier process than having to guess like, okay, if I was to put a chemical reaction here, then what happens? Like the previous way was a bunch of guess and checking, and then once you've done the guess and checking, then you go back to the literature and you just say, hey, I can actually justify this term I put in there, right? Like, but now you basically get a machine learning approach that says, write down the model that is for sure true. It gives you it and then kicks out a list where the scientist still has to be in the loop, right? Because you still have to have a real mechanistic model. But what it's doing is going to kick out a list that says, these are the 10 things that you should check, and we just do your checklist and go through the system. Then at the end of the day, you'll have a fitting model, and boom, right? So that
Mhm.
really brings down the process of discovery. Um, it was interesting then because I was working on it for the sake of equation discovery. But while doing that, then the MIT Caltech Klima climate model, it became a pretty big deal in the Julia lab. And so I started to talk with everyone. I started thinking, is there a way to do scientific machine learning on that problem as well? And there had to be, because I mean, most of the way that people are using scientific machine learning outside of what I was doing was more about surrogate acceleration of models, rather than model discovery. But it was interesting to be able to see that, after talking with them for a bit, it looked like this exact same idea of model discovery via universal differential equations is also what you want to be doing in the klima space, because you can phrase the klima problem as wanting to find a reaction advection equation, where you don't know what one of the terms of the equation are, and if you discover that, then you have a one-dimensional PD that approximates a three-dimensional PD, right? And then I mean that really let the cat out of the bag, because then I looked at like Hahn and Jensen's work on how do you solve 100-dimensional PDs, and oh, that's a universal SD. And that you look at Carniadakis and Razi's work on multi-step physics informed neural networks. So the continuous physics informed neural network is a completely different idea, but these discretized versions of physics informed neural networks actually are universal differential equations as well. So then it became like, oh, like you can, not only is this method something for um, for automated model discovery, but it's also for accelerating models. And it's, you can phrase a lot of these other methods that are coming out as the same thing. So what we can do is we can just work really hard to have one library that just does universal differential equations in its most optimized sense. And then once we've optimized that, we can implement, we can create a whole library of all of these different scientific machine learning methods by just phrasing them as a universal differential equation and then letting our previous tool handle it, right? It's a lot like the way that for example, stiff ODE solvers are used. So yeah, basically what you end up with is you have that one method, right? The universal differential equation that is kind of like the stiff ODE solvers of scientific machine learning, right? You basically can funnel many different methods into just this one method, and then we can sit there, have one optimized piece of code for it. Then it's 100 lines of code to be able to just write down and transform other methods into universal differential equations. And so that really is where the SciML ecosystem started, because what that meant was we could easily expand out to a whole range of problems, just by representing them as problems that are then trained and solved by diffie flux. Um, and so that let us expand fairly fast. And so before we were all about the differential equation solvers, but once we had diffie flux, we quickly went to something that was about also doing surrogates and also doing surrogates and model discovery and all these other pieces that make it scientific machine learning. And that's when the name change kind of happened. I mean, the other
Mm.
reason for the name change was that um, it was no longer Julia diffie because we now had packages in Python and R, and it was more than just differential equation solvers. So yeah, Julia diffie had to go, right? What
Mhm.
was it going to be? Well, the core underlying theme was that everything was being built to do a whole scientific machine learning ecosystem. So it made sense just to say let's just name it towards that. Um, yeah, and I think that this has been really successful, just kind of having this
Mhm.
focus on, there's still a major focus on building stiff ODE solvers and, optimizing them and everything. But with the aspect of knowing that differentiating through all the tools is very important, because that's the way that a lot of our users are using it in 2020. So.
Right. I see. I also see a lot of parallels. You also mentioned sparse regression, so I see parallels between your work in scientific machine learning and the sparse identification of nonlinear dynamics work by Stephen Brunton.
Yeah,
In
I would
fact,
actually, I would
I
say that Brunton and Kutz's work is scientific machine learning work, and we built
you
data-driven
think it's the
diffie.
same?
Well, I mean, it's one aspect of it, right? Like it's one
Yeah,
aspect of
it's a
doing.
subset because I applied I combined symbolic regression with sparse regression in one of
Mhm,
my papers, and so I was curious about your take on the differences between doing sparse regression with known symbols
mhm.
or doing it with neural networks, because I think that's the only difference. I mean, what's your take on that?
Well, so what do you mean by that? Do you mean like representing the basis functions as neural networks and then doing a regression against them, or?
Yeah, I mean, isn't that what the universal differential equation paper discusses?
No, so what the universal differential equation paper is really discussing is that there's two problems that you need to be solved, right? And one of the problem is, we don't want to do the sparse identification dynamical systems thing directly on data, because we know a lot of the chemical reactions, right? It goes back to that problem of, if we know that
Okay.
chemical reaction A to B exists, it better be there in the solution. So we need to change the problem for how we're doing the learning, such that that is going to be true. Um, the other aspect to it is that the Cindy paper and a lot of the papers in that domain assume that you have a derivative estimate, right? They assume
Hmm.
that you have a DUDT term. In a lot of realistic scenarios, you don't have that, and it's okay to not have that if you have dense enough data, because if you have dense data, you can interpolate. But if you don't have dense enough data, then the interpolation also gives you bad derivative estimates, right? Um, and especially in the pharmacology case, where you might have dense
Hmm.
data, but different patients have different measurements at different times, so you can kind of know that your curve, kind of like in some cases you can kind of know that your curve has a big dip and it goes up, but for any individual you might have a data point like boom, 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 and so one of them hits the dip, the other four patients don't hit the dip, but you know that your derivative should be having the dip. An interpolation isn't going to work, right?
Mm.
And on those kinds of problems, what you can still do is you can still train these universal differential equations where you're learning a neural network inside the
Just
differential
from
equations.
state observations without the derivative.
Yeah, just from the state observations, right? This is the same reason why learning ODEs can work, right? Just if you specify some of the dynamics, and you're only saying that this portion is the only thing that we don't know, then it can still kind of figure out that every single individual has to have that dip, right? There's certain things that's then able to find. And then if the problem is, then what the universal differential equation paper says is, what we can do at that point is we can do the Cindy-like method except directly on the neural network, because what we're actually looking for at that point is only to discover the missing parts of the dynamical systems.
Mhm.
And this lets, then the neural network is kind of like an oracle that is like a smooth derivative estimate at any place that we ask for it. And so it is both like an oracle that solves that derivative problem, but also it solves that problem of we've trained that neural network such that all of the information that we know that we wanted to be true, like all the other parts of the dynamical system, are already hard coded in that training process of the neural network. And so what it's going to give us is just the missing parts in the model that we didn't know.
Right.
So I wouldn't say that it's doing. I would say it's kind of an extension of the Cindy idea to kind of say
Mhm.
how would you want to do Cindy if you didn't have if you had sparse data and you wanted to incorporate prior information.
Right. Right. And you call it gray box instead of black box because as you said, you start by assuming a lot of things to be true, and you want your model to correctly identify that. So
Yeah,
you're,
exactly.
let's say,
Mhm.
you're not in the frame of mind of people using recurrent neural networks such as
Yeah,
LSTMs.
it's
You,
definitely not that frame of mind of neural networks where you're like, oh, I want to not specify any of my features or anything because the neural network's going to do better than me, right?
Mhm.
It's the other frame of mind where it's like I want to use as little bit of a neural network as possible because I don't trust neural networks, but I need to use one, right? Like I mentioned before, it's like it's the skeptic's way of doing machine learning, right? You're basically
Right.
just like I'm going to do as much of classical modeling as I can, but then I'm going to say like, oh, but I need to use a neural network, so let's put a neural network in here because I really don't know what's going on with my model, and now let's effectively use that to be able to get back to models, so that way it can also double check the model at the end. Um, yeah, kind of like a skeptic's machine learning in
Mhm.
some sense.
Yeah, yeah. I see. I see also a lot of ways in which this line of reasoning is pushing towards interpretable machine learning, in the
Mhm,
sense that people can stop seeing them as magic boxes, as many
mhm,
people say, or at the same time, you can, for example, deal with issues such as extrapolation performance or overfitting by
mhm,
saying, okay, no, I'm just using it. I'm not using it for everything. I'm using it for the small bits and pieces of my problem that I'm not aware of,
mhm.
and so I can leverage its staminal nature, let's say, and then I can solve the problem. I now frame it. Okay, thanks for the clarification. About that, I have a philosophical question.
All right.
So I already know your answer because you explained it,
Mhm,
but I want to say it out loud. So the issue is we have people saying the differential nature of dynamical systems is not going to be challenged by the rise of power of machine learning. Other people may say, not I'm not sure, but I'm devil's advocate here. Uh, may argue we don't need calculus anymore because we have machine learning. Do you think such an argument? There's room for such an argument,
oh,
or
that's silly. There's calculus in machine learning, right? I mean, the process of doing local optimization is solving an ODE that is defined by the gradient flow, right? Like, so the differential equations show up everywhere, even in machine learning. So they're going to be around forever. Um, Now, whether you need to write your model in a continuous sense, that really comes down to the properties that you're trying to predict, right? I think that a very interesting thing to point out is that continuous models actually have very different behaviors from discrete models, right? So, for example, you can prove that in one or two dimensions, you cannot have chaotic behavior in a continuous model, right? Because you have your flow lines, and if you ever hit a flow line, you have to go back on that flow line. You can't jump over them, right? You can jump over them in a discrete model. Um, that's one of, so your bifurcation theory is completely different, and your chaos theory is completely different, right? Between continuous and discrete models because of that fact, right? Because of the fact that you can't jump over the flow lines in the continuous model. Um, and so I think for that reason, like, discrete models have introduced aberrations in the way that they're working. I mean, that they can be predictive a lot of times, but this is one of the reasons why they're not able to completely learn and predict behavior, in a way that extrapolates well, because they just do not have the correct underlying qualitative behavior in the first place, right? Like, getting the quantitative result is kind of difficult if you know that it has quantitative problems, right, or qualitative problems. And so I kind of think that, I mean, that's why I kind of take, neural ODE architectures, or these deep equilibrium layers and everything. They're interesting architectures for machine learning to look at, because if your problem is continuous, these are the types of architectures that would make it so that way your model does not have these qualitative incorrect problems that can occur if you're to model a continuous system with a discrete system. Um, so I mean, and there's many cases that you can point to, and a lot of dynamical systems theory is about differentiating the behaviors between these two types of systems. So I think that a lot more of that literature might become, relevant and actually exposed and cited and seen more in machine learning in the near future, because of this direction, to kind of impose continuousness and show the value of having continuous model. So two reasons, right? Uh, in summary, like, you're always going to have the calculus in the training process. So I mean, boom, there you go. It's never going away. But also B, continuous versus discrete modeling actually has real qualitative differences. And I think that more so, to overcome some of the issues of machine learning, more of the models will need to become continuous. So.
Okay. Okay. Great to put. Okay. Okay. I will not look into LSTMs then in my research.
LSTMs, I think that the right analog to LSTMs is universal differential equations with delay differential equations in them.
Right.
The package is able to optimize them. We didn't put one inside of our paper because we actually didn't find a good example to do it with. Um, so like, it's kind of funny. Like, we have it working and you can train them, but we're just like, well, what is this thing useful for? But I mean, LSTMs do have a delay in there because of the way that it does memory and everything. And so I kind of think that, like, the true analog in the neural differential equation space to LSTMs is something with a with delay differential equations in there, and there's something worth exploring.